So you have a, so actually the flow in the, when you flow in the pipe, the big pipe water. So a force pushes a flat plate across in the x direction. Okay? So it's push or it's pull, the same thing. So the plate therefore move parallel to the x-axis. Calculate the force F and the shear stress how exerted at the bottom of the thin plate. At the bottom of the thin plate. In other words, what's the shear stress? This value here. At the bottom of the thin plate. So it's actually a flat plate problem. Right? And answers are given there. So just give some, but I won't do a solution here. So what is your approach? You just discuss the general approach. What's your approach? What do you have to use? Now I try not to work out a solution because if I work out a solution, then you do just copy, and then you need to, as I said, the Olympic, you need to train your brain to work out all the solutions. Because the Olympic is the exam, so to work through all this. Okay? Right, it gives some guideline or tell you approach. So what do you use? You're going to use the shear stress equation. Okay? How is this mu what? Remember the very first expression? Okay, so make sure you use that expression there. How is equal to for the viscous fluid, okay, you're going to use that. So how is going to mu dy. Okay, and what is tau? Tau is the shear stress. It's a stress. Okay, and this pulling, this force. How is therefore convert tau into F? Tau is therefore F over A. Okay? F over A will give you your shear stress. That's on the left hand side. So right hand side goes to mu. So what is the du dy? In this case, what's the du dy? The du dy is the plate velocity u over h. U over h. Okay? Because you are interested to find out about the force and the shear stress exerted on the bottom of the heat plate. At the bottom, the plate is moving. The shear stress at the bottom of the heat plate, the plate is moving. Okay? So you can start out with F over A. Big F over area of the plate. A is given there. Is equal to viscosity mu times big U over H. H is given there. Okay. And U given there as well. Yep. And then you put in the numbers. You'll be able to find F. F is the unknown there. Okay. So having found F, how do you find tau at the bottom of the flat plate? Tau is F over A. So you can find tau. Right? Okay. The second question is more interesting. You have second question. Okay, you are given this situation here. There's water flowing downwards. Okay, on a fixed surface, and that is your velocity profile. given by this expression here. Okay? Your velocity goes down is given by this expression here. In other words, this is the equation of this curve. Okay? This is the equation of this curve. Alright, you don't understand what it means, eh? Okay? So you're asked to find the magnitude and direction of the shear stress that the water exerts on the fixed surface when the mean stream velocity is 3 meters per second and the height is 0.1, given viscosity of water so much. So, in this case here, how do we go about doing that? How do you go about doing that? So how do you go about doing that? How do we start in this case here? Again, you're going to use the fundamental equation that links the shear stress with the velocity gradient. Tau is equal to mu, Lu, Ly. Tau is equal to mu, Lu, Ly. That's a very fundamental equation for viscous flow involving the shear stress. Okay? So once you put that in, what do you do next? Okay, you are given here the equation of this curve is given there. Then you have the equation that just put in. Tau is equal to mu, Lu, Y. So what's the Lu, Y? How do you actually put in something to replace of Lu, Y? Your Lu, Y was to come from here. This given expression here. Okay? So your Lu, Y will become from this expression here. You put U, you put U on the left hand side, the rest is on the right hand side, and then you differentiate to get del U over del Y. Okay? And once you got that, you just put in the numbers given to you in the question. You should be able to find tau, the shear stress that the water exerts on the fixed surface when U was 3 meters per second to 2.1. Okay? And you see that this is positive. It cannot be negative in this case here. You work it out, it's positive. Okay? So in other words, the shear stress is greater than 0, it's positive. So it's along the fluid direction. Along the fluid direction. Okay, so the direction of the shear stress is along the fluid flow direction. And its magnitude is given in the answer bracket there. 6 times 10 to the power minus 2 Newton. Alright? So I'm just giving you a guideline, the approach. You have to work it out yourself. Then question 3. Okay. Question 3 here says water flows through a pipe of diameter 4 mm at 3 meters per second. It's a flow of non-turbulent. Easy enough. What do you find? So what do you find in this case? Find the Reynolds number. Reynolds number. Okay. So if Reynolds number is below 2000 is laminar flow, more than 4000 is turbulent flow, between 2000 and 4000 is transition. Okay, flow transition. Okay. Then question 4 is, at what depth below the pressure of oil will be equal to 2 bar? Consider that the oil container is open as an atmospheric pressure, and the density of the oil is 600 kilograms per meter cube. And the depth is down to 16.77 meters. 16.77 meters. So what do we use in this case for question 4? Anybody? Anybody? So for question 4, this got to do with hydrostatic pressure. Hydrostatic pressure. If you use pressure at that particular point in question, this goes to T atmospheric plus rho GH. Okay? The pressure which you have to find, this goes to T atmospheric plus rho GH, and you get the answer already. Alright? Then for 5, what depth of oil with a specific gravity of 4.8 will produce a pressure of 120 kilonewtons per meter square? What would be the corresponding depth for water given the specific of water to be so much? Okay, so what depth of oil with a specific gravity of 4.8 will produce a pressure of 120 kilonewtons per meter square? This one will give it some thought, but it's not a difficult question. Okay, there's a few steps. You must understand what is specific gravity in the first place, which we have covered already. Specific gravity is basically the specific weight of a substance over specific weight of water at 4 degrees C. Okay? So basically, specific gravity basically represents how much heavier the given substance is compared to water at 4 degrees Celsius. And of course, you can use the specific of water which is given there, gamma, as 9.8 kilonewton per meter cube. Okay. So you have specific gravity is equal to the specific weight of that substance over specific weight of water at 4 degrees C. So the specific gravity in this case for that substance is oil is 4.8. So on the left hand side you have 4.8. 4.8 is equal to specific weight of oil, which we do not know yet, over specific weight of water, which we know is 9.8. So therefore, in this case, we can find a specific weight of water. Okay? So having found the specific weight of water, you need to use another relation to find HW, which is the relation that we use in question 4. In question 4, T is equals to P atmospheric plus rho GH. Okay, and so what is rho G? Rho G is actually gamma of oil. And gamma of oil you just found out already. You just got the answer for gamma of the oil. So the only unknown is actually H oil. So you can find H oil. This case is 2.3 liter. Okay? And next is work with the corresponding depth for water. With the same approach, you'll be able to find the HW for water. Okay? So please work on it. Thank you.